Okay, we worked on simplifying the radical expressions, some basic ideas, power matches index, take out the base. We're going to build on some information we've been working on we did with composition, the arithmetic functions, evaluating a radical function. So I could give you this, f of x equals the square root of x. This is a basic square root function. Okay, so we know this is a 2. So if we have this, we can go through and evaluate. So if I plug in, say 0, I can evaluate. That's square root of 0. Please make sure that we simplify this. Square root of 0. 0 could be considered a perfect square as well. 0 times 0 is 0. Well, the square root of 0 is just 0. So if I did f of 1, square root of 1 is 1. If I did f of 4, square root of 4 is 2. Now I can keep plugging in all the perfect squares. Okay, and square root of 9 would be 3, square root of 16 would be 4. But again, if I did something like this, we evaluated this one earlier. If I plug that in, we get square root of 17. This here, square root of 17, is an exact value. It maintains all your decimal places. Okay, but if we were to take this and consider thinking of this as a collection so that we could graph, we plugged in 0, we got 0. We plugged in 1, we got 1. We plugged in 4, we got 2. Plugged in 17, we know we had, I think it was 4.123. We could use that. We could use those and start collecting data for a graph. What about f of negative 5? Well, if I look at that, I get the square root of negative 5. Hopefully you're saying that you realize that's an even index, that's a negative radicand. This is a no real solution. There are no two numbers in the real number system that I can multiply together to get the negative 5. Okay? So if you look at this, if you think of these values as ordered pairs, we plugged in 0, we got 0. Plugged in 1, we got 1. Plugged in 4, we got 2. We plugged in 17, we got 4.12. We go through. If we have enough of these, we can start graphing. The basic radical function looks like this. If this is our graph, it starts from 0 and goes off in that direction. Okay? So we should be able to take a function. Now they're going to be more involved in these. And we should be able to evaluate. If I give you a value, plug in evaluate. If it says evaluate to so many decimal places, it's probably because it's something like this. All right? Now, as we alter this, we add stuff inside. What you'll see is this graph will shift left, right, it'll expand. If you see stuff added or subtracted after this function, you'll see that graph translate up or down. Okay? Let me go through. I want to give you another one in this clip and go through some evaluating. And some other information. So if I have f of x equals square root of x plus 5. If I ask for f of 4, this becomes square root of 4 plus 5. Now remember, evaluate inside first. Treat this as a parenthesis, evaluate inside, and then look to simplify. Well, 4 plus 5 is square root of 9. Square root of 9 is 3. We do not want to try to take the square root of 4 and then the square root of 5 and then add them. Work inside. So an ordered pair for this would be 4, 3. I plugged in 4, I got 3 out. Well, we can go through and we can repeat that. What if I plug in negative 7? Well, it gives me negative 7 plus 5. That gives me square root of negative 2. Hopefully you're saying, well, that's a no real solution. Even index, negative radicand. I wouldn't be able to use that value to graph. And that kind of builds in to the another concept. If I look at this, yes, it's over 1 for that function, so I can start thinking of domain Well, I have to look for look at the denominator, see if there restrictions. Well, this is over 1, so there's no restrictions in that sense, but there is a restriction in the fact that I have to keep this value to be positive. Okay? So what we can do, if I have something like this with the square root, I can find the domain of this without having to graph it. Now, ultimately, we worked with those graphs where we had the graph and we looked left to right for the domain, we looked low to high for the range. But if we had this to save you time instead of having to calculate a bunch of points, draw the graph, and then evaluate, here's the trick. When I have this, I can take the radicand, okay, the radicand, oops, got to spell. I can take the radicand, and I can set it to greater than equal to the last value that I could calculate. Well, basically, I don't want it to be negative. I want it to be 0 or above. I want it to be something I can calculate. So it's got to be greater than equal to 0. So every time I had this, even if it was just the square root of x, I could set it greater than equal to 0. So when you look at that graph that I had erased, it started at 0, went to the positive. Well, again, as I add things in here, it's going to shift it right or left. Well, if I take x plus 5, that's my radicand in this instance, and we only want to do this when this is a 2. We only want to do this with the square root functions. If I take that and set it greater than equal to 0, if I solve that, I can find what the domain is. That's useful so that I know that if I go to select some values, that if I go to plug it in, I know it's going to be a no real solution. So if I solve this, remember, we've solved inequalities, subtract 5, I get x is greater than equal to negative 5. Well, for set notation, if you were asked for that, to remind you of that, just add the curly brace x such that x is greater than equal to negative 5 in interval notation would be a bracket, because that's an equal to, negative 5 to infinity. Remember, with the infinities, we use the parentheses because we cannot get there. That would make sense. That would tell me that if I tried to plug in negative 7, it wouldn't work. Negative 7 is further to the left than negative 5. Negative 7 doesn't fit into that. So I would start at negative 5 as my first value, and whatever value I get here is always the value that's going to get us back to 0, and then anything to the right of it. Okay, we can have it where it does flip. It does go the other way, where we can have a less than or equal to, because the graph then would go opposite. Okay. Here's what I want to do. I'm going to stop this one and then start a new one. We'll do a cube root function, talk about the domain of that and how you can find it. And it ties back to some stuff, and then it'll get a U-try problem from it.